AP Chemistry, we're now moving on to part 3 of the answers video for the winter packet, and that's going to begin with question 25. So this problem is an empirical formula, and this is the type that we dealt with originally in class. There are 2 other types, and we're going to be sure that you're proficient in all 3. But what the idea of an empirical formula is to determine the lowest ratio, somewhat like a formula unit for an ionic bond. It's kind of like that for a covalent bond. It's the lowest ratio of the elements, in this case a hydrocarbon, a CH compound. And then using that and knowing one more piece of data, the molar mass of the substance, without even knowing what the substance is, that can be done, then you can determine what the substance is. You can identify it, okay? So this one involves a few steps, and again, eventually you learn to do these in a way that you can do them on the AP without all these boxes, okay? The boxes are just there to help you along the way. Okay, so what we want to find out is how many moles. Remember, chemical equations are always in moles, not in grams. So how many moles of carbon do we have, and how many moles of hydrogen do we have? All right, so we're starting off, we look down here, we're starting off with numbers of grams of CO2 and of H2O down here. We need to get those into moles. So the first step is you're going to write these number of grams into the respective boxes here. So for CO2, it's 33.01. For H2O, it's 13.51. Okay. So now what we need to do is do a molar mass conversion to get this into moles of CO2 and this into moles of H2O. But I'm not going to have you do that as I did on the assignment originally when we did this as a separate step. I'm just going to have you incorporate it into the 2-step equation. So we need to go from grams of CO2 using the molar mass to moles of CO2, and then from moles of CO2 we need to go to moles of carbon. All right, so if we see carbon there, we see that, I'm going to go ahead and write coefficients and subscripts where you don't see them. If we have 1 mole of carbon dioxide, and for every mole of carbon dioxide, even though you would never normally write this 1 here, you have 1 mole of carbon. So 1 mole of carbon for every 1 mole of carbon dioxide. For water over here, we're going to start with the grams. We're going to use the molar mass to convert to moles of water. And then from moles of water, we want to get to moles of hydrogen. And we can see that for every 1 mole of water, we have 2 moles of hydrogen. Okay, so we're going to go ahead and use that 2-step equation to figure out how many moles of carbon and how many moles of hydrogen. So we'll come down here and do that. And this one is just for the carbon dioxide, so we're going to start with this. Okay, so we start with 33.01 grams. We're using the molar mass of carbon dioxide to get to moles of carbon dioxide. So grams of CO2 cancels. And then we're using the relationship that there's 1 mole of carbon for every 1 mole of CO2, as we just saw up at the top. And so now it's just time to do the math. Moles of CO2 cancels there and there. Last man standing is moles of carbon. So we'll go ahead and calculate that. Okay, and what we get is 0.75 moles of carbon. Okay, so we're going to go ahead and we're going to come up here and we're going to write that here because this row represents moles of either hydrogen or carbon. Okay, so it's 0.75. And what we see is that all the carbon that appears on the product side is here, and all the carbon on the reactant side had to come from here. So this number of moles has to be the same as that number of moles. So I'm just going to draw a quick arrow over like that, and it's going to be 0.75 right there. Okay, now we're going to come down here and we're going to do the same thing for water. So we start off with 13.51 grams of water. Okay, we do our cancellations. Moles of H2O. Notice again that there is 2 moles of hydrogen for every 1 mole of H2O. So we'll go ahead and do the math on that. And we come up with 1.498, which we're going to round. That's close enough to 1.5, and that's moles of hydrogen. right there. So now we're going to come up here and we're going to put that 1.5 right here. All right, and all the hydrogen that's on the, that's all the hydrogen you find on the product side, so that's all the hydrogen, and all of it had to come from here. That's the only place on the reactant side you see hydrogen, so we're simply going to draw this arrow over here like this, and put the 1.5 there. Okay, all right, so that gives us our moles of carbon and our moles of hydrogen to work with. Now we're going to go to work working on the empirical formula. Okay, so step D says make a ratio of moles of carbon and moles of hydrogen with the smaller number on the bottom. So the smaller number is the carbon, that was the 0. So for carbon, the ratio is 0.75 over, and on top is 0.75. The smaller one is always going to turn out to be 1, that ratio. For hydrogen, we had 1.5 moles of hydrogen, and we put that over 0.75, and that equals 2. Okay, so for every 1 carbon, we have 2 hydrogen. Okay, and the next step, E, says if you do not have whole numbers for both, multiply each ratio by whole numbers 2, 3, 4 until you have whole number of both, really, okay? Well, we have whole numbers of both. So we have, for C, we have 1, and for H, we have 2. We just calculated that. So the empirical formula is going to be C1H2, or we'll just call it CH2. That's the empirical formula. All right, now if we know one more piece of data, and that's the molar mass of the compound, and again, there is a way to determine that without knowing the compound, what its molar mass is. And we've talked about that in class briefly. We'll talk about it again in the future, but we won't worry about it now. But it turns out the molar mass for the actual compound is 28.06. Compute the molecular formulas as follows. So compute the molar mass of the empirical formula from part H. I don't know what that's wrong. Okay, so it's this. So what's this molar mass? You have 1C times 12.0201. And if you multiply those out, 2.02, 12.01, you're going to get 14.03 grams per mole for the empirical molar mass. Okay, we don't know if this is a real molecule or not, but we don't need to. We're going to determine what the real molecule is. All right, so there's the empirical molar mass. That's called the empirical molar mass. Okay, and then there is a formula, and the formula says that we're going to find a factor called N. It just means a number, a factor. And it's the empirical molar mass, the molar mass. So the molar mass, which we were given, is 28.06. And the empirical molar mass is 14.03. And if you divide those, you get exactly 2. So that's our factor. That's the N. So what that means is you're going to take that number and multiply the subscripts of the empirical molar mass to get the actual molar mass of the real world molecule. And so we're going to come down here and say C1 times 2, H 2 times 2, and that equals C2 H4, and that is an actual real world molecule. Okay, so that's how you do an empirical formula. If you practice them 3 to 5 times, they'll be very natural. Okay, you just have to practice. All right, we're going to move on. It says give the names of the following covalent compounds. You will learn how to construct covalent molecules in a later unit. Okay, so this was something we did back when. Okay, so for covalent molecules, you got to remember these are the ones that use the prefixes. So 1 is mono, 2 is di. Okay, 1 is mono. Get back on screen here. 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 hepta, 8 octa, 9 nona, and 10 deca. And don't use this one. Don't use mono on the first element. Okay, so NO is not mononitrogen monoxide, it's simply nitrogen monoxide. Okay, so we'll do that one together. The first element in the compound does not change its name. Nitrogen remains nitrogen, and the second element adds IDE, changes to IDE. So nitrogen, it should be monoxide. You do use the mono on the second element. And it's not monooxide, it's just monoxide. You drop one of the O's. Okay, that's it. Okay, let's do this one. So try to do these before me. See if you can just go ahead and use these. All right, so this one is going to be bromine, and 5 is bromine pentafluoride, IDE. Bromine pentafluoride. This one, again, stop the video and do these yourself first. This is phosphorus trichloride. This is dinitrogen, because it's not simply one of them, it's two. Dinitrogen monoxide. This is disulfur dichloride. And this is diphosphorus pentoxide. I don't want you going on Google and looking this up and getting nitric oxide, okay? That's a wrong answer. I want you to do it using this naming convention, okay? Don't worry about what Google says it is, okay? So learn this naming convention. So again, it's covalent bonds. Those are non-metal covalent bonds. They use these prefixes. Ionic bonds do not use these prefixes. All right, we'll go on. All right. Okay, now we're going on to ionic bonds. So in the left column, you see metals, and in this column, you see nonmetals. So nonmetals, metals, strong guys, weak guys. The nonmetals take electrons away and become negatively charged anions. So I want you to write that down. Let's start with metals. Metals. Okay, so metals give up electrons to become positively charged cations. And now nonmetal, I'll say it and you write it. Nonmetals gain electrons to become negatively charged anions. Nonmetals gain electrons, they take on a negative charge because they have more electrons than protons, and that makes them negatively charged anions. Okay, so the way we do these is the crossing arrow method. So you write the charge above each of these. So nitrogen, sodium has a +1, oxygen has a 2-. So I wrote it right here, sodium +1, oxygen 2-. So you cross the arrows and you get Na2O1, or just Na2O. And that's sodium oxide. It is not monoxide. We do not use the prefixes with ionic bonds. Okay, just something you have to remember through practice. Okay, next we come down here and we have calcium has a 2+ charge. Again, you need to learn to do that from your periodic table, not from charge number of ions. There's calcium right there. It's in the second column, so it has a 2+ charge. Phosphorus is in the third to last column, 1, 2, 3, so it has a 3- charge. So you put those charges above and then you cross the arrows. So you end up with calcium 3 from the phosphorus and phosphorus 2 from the calcium, and that's calcium phosphide. Okay, let's go down the rest of them. So strontium has a 2+ charge because it's in the second column. So strontium 2+. Chlorine is in the second to last, so it's going to have a 1- charge. So it's going to be, let's go ahead and just do that one. 2+. Chlorine is 1-. So I'm going to write that down here. So the 1 goes up there underneath strontium, the 2 goes up here under chlorine, and so it becomes SrCl2, and that's going to be strontium chloride. Okay, gold. Now you have to be told gold. This one you have to be told because gold, which is Au, and you would need the charge number by ion sheet, but you don't need it really here because I'm giving them to you. But it would tell you that gold could be a +1 or a +3. Okay, so gold is a transition metal that has more than one possible charge. We're going to use the 3+. Fluorine from your periodic table. Without using charge number by ion, periodic table, you should be able to tell it's a 1-. So the 1 crosses over to the gold, the 3 crosses over to the fluorine, and what you're going to have is AuF3. AuF3. You need 3 of the minus charges to balance that 1 3+ charge. And that's going to be called, let's write this one out. This is different. When you write it in words, not when you write the formula, it's gold 3. It's not the number of atoms, it's the charge on the gold atom. Gold 3 in parentheses, fluoride. Okay, so I want you to show all this like I showed up here. I'm not going to write everything because I don't want you copying. I want you to be thinking this through, okay? Don't want this to be a copying exercise. Okay, titanium has more than one possible charge. Okay, so it has a 4+ charge. Oxygen has a 2- charge. So you cross the arrows and you get Ti2O4. Okay, Ti2O4. 2 on the oxygen, the 4 on the titanium, you cross them over. Ti2O4. And so that's going to be titanium, Roman numeral 4, which is IV. And I'll go ahead and write it out here. And oxide. Okay, titanium 4 oxide. Okay, just 2 more. Zinc. Okay, I didn't put a charge on zinc, so it must have just 1 charge. Okay, and you can look at your charge number by ion. Since it's a transition metal, you need to do that. Or your 60 common ions has zinc also, and it's a 2+. So zinc is a cation 2+. Oxygen is a 2-. You crisscross the arrows, and you get zinc 2O2. However, it's the lowest ratio. If it's a 2-to-2 ratio, then you can simplify that, like reducing a fraction, and it becomes a 1-to-1. So it's just ZNO. 1 zinc for every 1 oxygen. Since there's not more than 1 possible charge on zinc, you do not use a Roman numeral, even though it's a transition metal. So it's simply ZNO, and it's zinc oxide. All right? Nickel. Now nickel has more than 1 possible charge. We're saying we're going to use the 3+. Sulfur has a 2- charge. So this is 2-, this is 3+. You cross them, and you end up with nickel Ni2S3. Okay, Ni2S3. You need 3 sulfurs for every 2 nickels. Okay, and since it does have more than 1 possible charge, it's going to be nickel, Roman numeral 3, that's III, parenthesis, sulfide. Okay, nickel 3 sulfide. All right, that's how you do those. Again, go back and watch the video on naming compounds if you don't remember this, okay? Okay, now we're looking at some ionic compounds with molecular ions. These are the ones that are covalently bonded molecules, but they form an ionic charge, and therefore form a charge rather, and therefore that charge can be used to form an ionic bond. So SO4 is a molecule. It's covalently bonded, but it ends up having an ionic charge. And this happens because they're dissociated acids, bases. We'll get to that in a later lesson. So it's a 2- charge. That means it can form an ionic bond with a cation. All right, so sodium has a 1+ charge. Sulfate has a 2- charge. So you can go ahead and write, you can just write it right here if you want. 2-, 1+, and you cross the arrows like that. And what you end up with is Na2SO4, sodium sulfate. Okay? So there's a 1 at the end. If you put it in parentheses, there's a 1 at the end there, but you don't have to do that. So it's Na2SO4. All right, and that's going to be sodium sulfate. All right, let's go to this one. Calcium has a 2+ charge. You know that from the periodic table. And carbonate has a 2-. Now there's a mnemonic I gave you, but we haven't talked about it a lot. And it's BINC SCP. Okay, write that down. These are all 1 minus charges. These are 2 minus charges, and phosphate is a 3 minus charge. So what are these? This is borate, and that's Br3 minus. Okay, next is iodate, and that is IO3 minus. Next is nitrate, and that's NO3 minus, and all 1 minuses here. Now the 2 C's you got to keep straight. This one is chlorate. And that's ClO3 minus, and I forgot to put the O here. So notice these are all, if you're trying to remember how many oxygens, these are all 3s. They're all 1 minus, and they all have 3 oxygens. Okay, this is chlorate. Now we come over to sulfate. SO4, that has 4 oxygens, 2 minus. And carbonate. And that's CO3, 2 minus. Okay, and then finally we have phosphate, and that's, write that. Get on screen here. And that's PO4, 3 minus. So for the charges, remember BINC, SCP. However you remember that, BINC, SCP. And then for the number of oxygens, all of them have 3 oxygens except sulfate and phosphate. That's all you have to remember. They have 4. Okay? Alright, so we're going to come back here. And we have calcium carbonate. So again, it's a 2 minus and a 2 plus. So that's simply going to be CaCO3. It's a 1 and a 1. So you don't have to write the ones. And it's calcium carbonate. Okay, let's talk through the last 2. You write them down. Potassium and nitrate. So nitrate is an N, is a part of BINC. So it's a 1 minus. I gave you that. So it's KNO3. KNO3, and that's potassium nitrate. Just simply put those 2 words together. Okay, finally we have sodium nitrate. Okay, so it's NaNO3, and that's it. And that's sodium, and it's sodium nitrate. All right, so that takes care of the naming. Okay, now we're going to move on to question 26, and this deals with the topic of solubility rules. How do we know whether an ionic compound will dissolve in water or not? And you'll find this, the lesson is day 49, net ionic equations, and it's at the beginning of that video. Okay, so that's where you'll see this, and I put a copy of this video in the winter assignment packet. All right, so how do we do this? We look at these, and let's do a few of these together. So KCl. So these are the ones you really have to know above all others, are these up here. So it's lithium, sodium, potassium. So notice those are in the first column of the periodic table. They're alkali metals. And then you have what's called ammonium. It's a conjugate acid of ammonia, and nitrate. And this is acetate. We don't see that one that often, but it's there. I really think, though, you should know these, because these are the ones that are going to determine whether something becomes a solid, whether it's insoluble and becomes a precipitate. So, for example, chlorine is soluble with anything except these 3 elements. So if you have lead chloride, then that's going to be insoluble. That will form a precipitate in the net ionic equation. Same with sulfate, okay? Sulfate's soluble with everything except 5 elements, and there they are. So if you had a compound that produced silver sulfate, that would be insoluble and that would form a precipitate. So you should memorize these, and I've asked you to do that as part of this winter packet. Is just write them down over and over and over again. These over here, carbonate and phosphate, are insoluble with anything except these up here. Okay, so they're insoluble. These are insoluble with anything except these and these. So for these two, it's these 3 and these 4. So anything will dissolve with these 4 cations right there. All right, so I do ask that you have those memorized by January the 17th. Okay, all right, so let's get going on some of these. So KCl, K is here, it's soluble with everything, so KCl is soluble, and I'm just asking you to write an S or an I. AgCl, so we come here, there's Cl, it's soluble with everything except 3 exceptions, and Ag is one of those exceptions, so it's insoluble. Okay, and so all of these in these first 2 columns are on that video. So go ahead and watch that video. All I want you to do is say whether they're soluble or insoluble. Okay, now we come over here to strontium hydroxide. Okay, so hydroxide is insoluble with everything because it's in the insoluble column, except these 4 and these 3. And strontium is one of these 3 down here, so that is soluble. Calcium carbonate, that's seashells. So right off the bat, you should know that that's insoluble. Okay, this is mercury bromide, that should be a lowercase r. So mercury Hg, or excuse me, bromide is soluble with everything except 3, and Hg is one of those 3, Hg2 specifically, so that's insoluble. And then KCO right away, there's K, it doesn't matter what it's with, that's going to be soluble. And AlPO4, so phosphate is insoluble with anything except these 4 up here, and Al is not one of those, so that's insoluble. Alright, so you go ahead and complete these based on the video. Okay, now we are going to do a net ionic equation.